So I put some problems together that are different from all the ones in the book, so that we could like see some variety. So we'll kind of look at those as well as like work on some of the homework problems today, which I put some more on the Moodle like 30 minutes ago or something. I don't know. Okay. So the first thing that I want to do is maybe recall this first isomorphism theorem. So this is pretty important. So I assigned that like really long video, but I made it skippable with like just a ton of examples. So it's useful to look at least some of those examples just to get a feel for what's going on. But basically the idea is you can find all of these isomorphisms between groups by figuring out a homomorphism and then figuring out the kernel. And then you've automatically got like an isomorphism involving a quotient group. So let's see what we've got. Let's say that G and H are groups. And phi goes from G to H is a homomorphism. Then we have the following isomorphism that is like induced from this homomorphism. So it goes like this. G mod the kernel of phi. So like I said last time, we showed that the kernel of phi was normal. And anytime you show that you've got a normal subgroup, the next thing that you should do is start thinking about what the quotient group is. Well, what's the quotient group? It's the image of phi. So this is isomorphic to the image of phi, and the image of phi is a subgroup of H. So this is like the nice, important, powerful first isomorphism theorem that gives you a lot of like leeway to find nice isomorphisms between groups. So let's maybe go ahead and write one more kind of usually onto this. Now this isn't always, but it's usually. Is that spelled right?
Yeah.
Okay. Usually, phi is surjective. What I mean by usually is in practice, like if you're setting something up, G is usually phi is usually surjective. But that means that the image of phi is the whole group, right? But that gives you this nice isomorphism. G mod kernel of phi is isomorphic to H. I got these new socks, guys. Look at these things.
Oh wow, what are they, flip socks or something?
They're Bombas. Bombas socks.
Yeah, I remember those socks they were on GTA.
They're a delight. I
Highly recommend.
highly recommend. 10 out of 10. I wore through all my other socks. Okay, so let's do an example. Well, some examples. So let's do this example. Let's define phi from Dn to Zn like this. Wait, no, sorry, Dn to Z2 like this. So we're going to take R to the identity, so that would be 0, and we're going to take S to 1. So in other words, we're going to take an arbitrary element, which is like S to the A, R to the B. That's going to go to A, right? So remember, A here can be from 0 or 1. And then B is from 0 up to n-1. Like every element of Dn can be rewritten like that. Okay. So previously we checked that this was a homomorphism. It's like not too hard to check that this is a homomorphism. Now, now what we want to do is see what the isomorphism theorem tells us about this. So let's find the kernel. So the kernel of phi, so that's going to be everything in Dn that is sent to the identity over in Z2. But notice that's going to be all powers of R, right? Yeah, so that's going to be all powers of R. So that's going to be R to the K, you know, for K in the set 0 to n minus 1, just by the definition of our mapping. Okay, but notice that that is the same thing as the cyclic subgroup generated by R, right? So the kernel of phi is the cyclic subgroup generated by R. Another thing that we notice is that this is onto, I'll put another little arrow there to mean that that's onto. We only have to land onto two elements, and we do, 0 and 1. But then by the first isomorphism theorem, this immediately tells us that Dn mod the kernel, but the kernel was equal to this cyclic subgroup, is isomorphic to Z2. That's all we had to do. Okay, let's do another. Okay, so let's look at this example. We want to show Z cross Z mod the following. It's not really a cyclic subgroup, but it's like a product of cyclic subgroups like this. So it's going to be the cyclic subgroup generated by M0 cross the cyclic subgroup generated by 0 n. Yeah. So we want to show that that is isomorphic to Zm cross Zn. Okay. Okay, well, how can we do that? Well, we could do it just by like calculating the quotient group, but calculating the quotient group on its own is like kind of a bummer. So we'd like to use the first isomorphism theorem instead. That gives you some nice like machinery to do this calculation a little bit easier. So let's do that. We want to define some sort of homomorphism from Z cross Z to Zm cross Zn in a way so that the kernel of the homomorphism is this product of cyclic subgroups of Z cross Z. Okay, so how could we do that? Well, let's take an arbitrary element from Z cross Z. So we'll take an arbitrary element here. Maybe that would be A, comma, B. And we've got to figure out where to send that. Well, since we're going from Z cross Z into Z M cross Zn, which is like, we've got the same sort of flavor of a group of the group, right? It's a finite group now instead of an infinite group. Maybe since we're dealing with Z and Zm, maybe we'll put brackets here. So this would be like bracket A, bracket B. Just, you know, for the sake of art, just to make it look a little bit different, right? So over here, these are just plain old integers. But over here, this one is an integer modulo m. This one's an integer modulo n. So let's say m is like 5 and n is like 4, right? Well, that means that if you add this thing to itself 5 times, you're going to land back at 0, right? So 5 is equal to 0, 10 is equal to 0, 15 is equal to 0. And then over here, if you add something to itself 4 times, you're going to get 0. So 4 is 0, 8, 12, negative 16, all those are equal to 0, right? So that's what's going on here. So I'm just like using this like little extra notation here of the bracket just so that it's okay. Okay. Now let's check that it's a homomorphism. So that means we need to look at the operation on the left-hand side, act on that by phi, and see that the operation is preserved on the right-hand side. So let's do that. We've got phi of AB plus CD. All right, so that'd be like the operation on the left-hand side, that sum of ordered pairs, but that's just done entry-wise. So that's going to be phi of A plus C, B plus D. All right, so that operation is happening inside of Z cross Z. But now this, by the definition of phi, is going to be the equivalence class A plus C, B plus D. Like I said, from the definition of phi, but then much earlier in the class, like halfway point or just before halfway point, we showed that the sum of equivalence classes was the new equivalence class defined by the sum. So that means you can pull this apart into equivalence class of A plus equivalence class of C, equivalence class of B plus equivalence class of D. Remember, we showed that like if A was congruent to C mod N or whatever, and B was congruent to D mod N, then if you added them, you still had congruence modulo N. So that's that. Okay. But now we can pull this apart into the ordered pair A, B. I should say equivalence class A, equivalence class B, plus equivalence class C, equivalence class D. But then that is phi of AB plus phi of CD, where this plus is happening inside of ZM cross ZN. So we're good. It is a homomorphism. So it's a homomorphism. That means that the group mod the kernel is isomorphic to the image, but we would like the image to be everything, right? So that means that we need to check that it is surjective as well. So let's do that. So let's check surjective onto. But there's not really much to do here. We just have to take an element from ZM cross ZN and find someone that lands on that. So let's take equivalence class A, equivalence class B from the target space, that's ZM cross ZN. So notice, because we're in ZM cross ZN, that tells us something about the values of A and B. Notice that A needs to be between 1 and m minus 1, and B needs to be between 0 and n minus 1, I should say. Right. We don't need any larger numbers because we're in ZM and ZN. And once you get to the point where you're at m, you're back at 0, right? M plus 1, you're back at 1. Okay. But now, just by this definition over here, we clearly have a pre-image, right? So now just observe that AB is just an integer. So if those equivalence classes come from ZM and ZN, then just AB is an integer. And phi of AB equals, well, kind of what we want it to equal. Equivalence class A, equivalence class B. So it is surjective. Okay, so we've got a map. The map is a homomorphism. It's surjective. Now we just have to find the kernel. Hopefully the kernel is this thing right here. So let's do that. Okay, so let's suppose, well, let's maybe make the claim. Let's do it like this. Let's claim the kernel of phi is equal to this subgroup right here of z cross z. So that's going to be the cyclic subgroup generated by M0 cross the cyclic subgroup generated by 0n. Like I said, it's a subgroup of z cross z. And then we're going to show that it's the kernel of a homomorphism, which immediately means it's normal. Although we already know it's normal because everything's in a abelian group. So all subgroups of the abelian groups are normal as well. Okay, so that's our claim. So let's just prove this like the old-fashioned way by containment both ways. Okay, so let's maybe do this reverse containment first, because I think that's a little bit easier. So let's suppose that AB is inside of this subgroup. So that's the cyclic subgroup generated by M0 cross the cyclic subgroup generated by 0n. I'm going to give myself a little more room. Just a little bigger. Suppose AB is inside of the cyclic subgroup generated by M0 cross the cyclic subgroup generated by 0n. Well, what does that mean? That means by definition that little a is in the cyclic subgroup generated by M, right? So notice that the A entry is the first entry, but the first entry is the one that's generated by M, right? And then that means that B is in the cyclic subgroup generated by N, because it's the second entry. But being inside this cyclic subgroup means that it's a multiple of M, right? Remember, this cyclic subgroup is like M, M plus M, M plus M plus M, M plus M plus M plus M plus M, right? So it's multiples of M, suffice it to say. So that tells us that A is a multiple of M. So it's going to be mx, maybe, mx, or some integer x. And then likewise, if B is in the cyclic subgroup generated by N, and remember it's an additive group, which is why I'm saying N plus N, N plus N plus N, and not N to the second power or whatever, because like it's additive, then that means that B is a multiple of N. So maybe B is equal to NY, where Y is some integer. Okay. And then let's look at our goal. Our goal is for this to be the kernel, right? So let's take this thing with our new version of it, mx and ny, and plug it into phi and see what we get. So we'll do phi of AB, which is the same thing as phi of mx ny now. Let's maybe just go ahead and point out that that's AB. And then by our definition over there, that goes to equivalence class of mx, equivalence class of ny, right? But look, we're working inside of zm cross zn, but that means that the equivalence class of a multiple of m is the same thing as the equivalence class of 0, right? Yeah, so think about like, if you're working in Z12, the equivalence class of 36 is the same thing as equivalence class of 0. So 36 is the same as 0. So same thing's going on here. So this is the same thing as the equivalence class of 0, equivalence class of 0. But now the fact that AB gets sent to the identity, that's the identity, right? The fact that AB gets sent to the identity, that's exactly what it means for AB to be in the kernel of phi. That's the entry phi to be in the kernel, is that you get mapped to the identity. So let's see what we've got. We started right here. AB is in this cross product of cyclic groups, and we ended right here. AB is in the kernel, but that's exactly what we wanted to show this containment, right? Yeah. Just by tracing the elements through. So let's look at the other direction. I mean, we're like really doing all the steps here, but I think it's like good. Okay, so we need to show the other containment. So let's do that. So that's going to go that way. So we're going to do the containment that way. So let's suppose that AB is in the kernel of phi. Yeah. And then we want to get to the point where AB is in this thing, right? Okay. Well, let's see what that means. That means that phi evaluated at AB is equal to the identity over in Zm cross Zn, right? That's what it means to be in the kernel. You get mapped to the identity. But the identity over in Zm cross Zn is 0, 0. But really like equivalence class 0, equivalence class 0. Okay. But by our definition of phi, this is equivalence class A, equivalence class B. Okay, but that tells us that in Zm, remember that this first entry is happening in Zm and the second entry is happening in Zn. So in Zm, equivalence class A is the same thing as equivalence class 0. But if equivalence class A is the same thing as equivalent class 0 in Zm, that means that A is congruent to 0 mod M, but that means that A is a multiple of M, it's equal to mx, right? So being congruent to 0 mod M means that you're divisible by M, which means you're a multiple of M, but that means that A is inside of the cyclic subgroup of the integers generated by M. So we're just like sort of doing this in reverse because it works the other way as well. Now we can do the same thing in Zn. So in Zn, equivalence class of B is going to be equal to equivalence class of 0 because of this line right here. But that means that B is congruent to 0 mod N. But that means that B is equal to ny. And I should be putting here for some y, which is an integer. And this is for some x, which is an integer. But now, B being a multiple of n means that B is inside the cyclic subgroup generated by n, inside the integers. Okay. But now what do we got? We have A is a multiple of is in the cyclic subgroup generated by M, B is in the cyclic subgroup generated by N, but that means that the ordered pair AB has got to be inside the cyclic subgroup generated by M cross the cyclic subgroup generated by N. Right? Because A comes from this one, right? And then B comes from that one. But notice we started with AB in the kernel. We ended with AB as in that, because so that finishes that the kernel is equal to what we wanted it to be equal to. And now we're home free. And we can just write down the answer after doing all of that. So finally, so first, isomorphism theorem will tell us that C cross Z mod kernel of phi is going to be isomorphic to image of phi. But now replacing the kernel of phi with what we just showed it to be, that's z cross z mod, what we wanted it to be, m0 cross 0n. Right? Sorry, guys.
Mr. Faulty.
I know. That's the kernel. That's what we just got finished showing it was, right? And then the image was zm cross zn. That's another thing that we showed earlier. We showed it was surjective, right? Which means the image is everything. So in the end, if you follow that horseshoe and just look at this bit of it, kind of complete the diagram, we get the isomorphism that we wanted to. So is there a quicker way to do this? Maybe, but I think like leveraging the power of the isomorphism theorem is the cleanest way to do it. Like you don't have to muck around with operations and cosets or anything. Like you don't have to do any of that. You just have to like find a homomorphism, not an isomorphism, and then describe the kernel, which is a bit simpler than the other possibility. Okay, let's look at one more, and then I want to give you guys a chance to do a problem, and then we'll look at it and repeat. Okay, where's my sheet? There it is. So this one is shorter. So this is a question. And that is, if you take a map phi from Z12 to Z10, and you define it by phi of n equals 3n, is this a homomorphism? So let's just recall what we need. We would need phi of m plus n to be the same thing as phi of m plus phi of n, where this addition right here is happening inside of Z12, and this addition right here is happening inside of Z10. So you can definitely just prove this by checking it for this single case, but there's a result that was in one of the videos that was assigned that allows you to solve this very, very quickly. So let's look at that result real quick. This is one of those results that's useful to keep like in your sort of ready to go set of tools, because it makes some things happen very, very quickly. So let's recall this. If phi goes from G to H is a homomorphism, so kind of any homomorphism, then the order of phi of G divides the order of G, and this is going to be for all G in G. So remember, the order is how many times you have to combine an element to get to the identity, right? Yeah. It's how many times you have to combine. So look, the order of the number of times you have to combine phi of G to itself to get the identity has to divide the number of times you combine G with itself to get the identity. So, but that's going to be a problem right here. And we don't have to look too far. We just have to look for 1. We can just start at 1. So notice that we can answer this with a negative, and that's because the order of 1 is equal to 12. Let's just recall that this is happening in Z12, right? But the order of phi of 1, which let's recall that's equal to 3, is equal to, well, how do you find the order inside of Zm? Well, there's like a formula that we had before. It goes like this. It goes the order of the group 10 divided by the GCD of 3 and 10. So in general, what's going on here is that the order of D in Zn is equal to n divided by the GCD of 10. I think we did that earlier. But 3 and 10 are relatively prime, right? Yeah, so the GCD is 1. So this is equal to 10. So what do we got? We got that the image has order 10, but that does not divide the order of the original element, which was 12. 10 doesn't divide 12, right? Yeah. I mean, that's really all there is. Really all there is to it. Now, could you do it simpler for this single case and not use the tool over there? Yeah, I think you could. And maybe you could do it by setting n equal to 4 and see that something goes wrong. So let's set n equal to 4. And notice that that means that we're going to have phi of 0 is the same thing as phi of, wait, no, sorry. Did I mean 4?
Do you mean 3?
No, I mean 10.
Where'd you get 4 from?
I don't know, I'm all discombobulated. Yeah, let's set n equal to 10. Okay, then we're going to have phi of 10 is the same thing as 3 times 10, which is 30. Wait, no, never mind. This is I'm blowing it over here. Oh, I know. You can do almost anything here. So let's say we have a phi of 2. So that should be equal to phi of 1 plus phi of 1 if it's a homomorphism, right? So if it's a homomorphism, that's phi of 1 plus phi of 1. But that's equal to 3 plus 3, which is equal to 6 in Z10, right? But then that's also equal to 6. So now we've got to go bigger. I'm really sorry, everyone. Yeah, let's do 4. So let's do phi of 4. So that's going to be the same thing as phi of 2 plus phi of 2. If it's a homomorphism, it'll be phi of 2 plus phi of 2. But now we multiply this by 3 and we get 12, right? But 12 is equal to 2 in Z10, right? Mm-hmm. But now over here, this is equal to 6. Wait, yeah, 6 plus 6, which is also equal. Okay, forget what I'm doing right here. I'm really sorry. I'm having like a brain malfunction, and it's like just kind of throwing me for a loop. Okay, so let's maybe take a few minutes to try one of these problems. So I added some. Let's choose one so that we're all doing the same one so we can go over it and get something out of it. So last time we did 2. 3, 4, 5. Yeah, maybe 4 and 5. Let's try 4 and 5. So I'll give you guys like 5-10 minutes and then we'll look at 4 and 5. Yes.
Oh, Dr. Ben. Well, I wanted to tell you that like for our math group class, you're down section 12.1 multiples of 3 twice.
Sick. Okay. Well, thanks. I'll fix that before next class starts. Okay, now that I've had time to like think a little bit more, I realized what was going wrong here and we can look at this. So let's take this. So let's suppose phi is a homomorphism. And then we're going to get a contradiction. So maybe we would say by way of contradiction, let's suppose that phi is a homomorphism. And then the problem that I was making is you want to loop around on the domain side. That's where everything is going to go wrong if you loop around in the domain side. So let's notice that 0 is the same thing as phi of 0, right? Yeah, because 0 is 3 times 0. But that's going to be the same thing as phi of 12, right? Because 12 is equal to 0 inside of Z12. But now we can split this apart into pieces pretty much any way that we want. Let's split it up maybe like let's split it up like this. Phi of 1 plus phi of 11. Yeah, but phi of 1 is equal to 3, phi of 11 is equal to 33, right? Plus 33. That's equal to 36. But inside of Z10, 36 is the same thing as 6, right? So this is happening in Z12. And then this is happening in Z10. So let's look at the extreme left and right hand side and see what we've got. So notice that this big equation implies that 0 equals 6 in Z12, which is, sorry, in Z10, which is our contradiction. Okay, so sorry about that flub earlier, but it's kind of a nice way to see it. So like I said before, the trick is that you want to loop around in the domain. That's where everything is going to kind of go wrong. Okay, so I'll leave you guys back to trying those couple of problems, and then we'll look at those couple of problems. Okay, let's look at this first one. There's my tab. So it's got a map from Z to Z. It takes Z to 7Z, and it says find the kernel in the image. So let's do it. And I'm gonna like slightly generalize it. Let's say we've got this map from Z to Z, and it takes maybe, no, we'll just do it like this. Phi of n equals 7n. Okay. So first we want to show that it's a homomorphism. Right. So let's calculate phi of m plus n. So that should be equal to 7 times m plus n. Right. But that's equal to 7m plus 7n. Right. But then that's equal to phi of m plus phi of n. Notice that there's nothing that can go wrong with the order of elements here because this is an infinite cyclic group. Everything has infinite order, and this is also an infinite cyclic group. Everything has infinite order. So this kind of problematic thing that we had before can't happen now. Okay, so it is a homomorphism. We're good. And that just uses the distributive rule from elementary school or whatever. Okay, now let's find the kernel. So I think the best way to find the kernel is to say that you've got something in the kernel and then decide what shape that something has to be. So let's suppose that n is in the kernel of phi, but that means that that means that phi of n equals 0. That's what it means to be in the kernel. You get sent to the identity. The identity, since we're working over additive integers, is 0. But now we know what phi does, takes n to 7n. So that tells us that 7 times n equals 0. But then we're working in integers, right? So if 7 times n is equal to 0, then that means that n is equal to 0, right? So we've got n is equal to 0. Okay, so technically what we just showed here is that the kernel of phi is contained inside of the set just containing 0, right? Because we found that if we're in the kernel, then we have to be equal to 0. But really, like this containment is the same thing as equality when the right-hand side is so simple. So the kernel is, we would say that the kernel here is trivial. The smallest the kernel can possibly be is the identity element. And that's what we've got here. The kernel is the identity element. Okay, now let's look at the image. Well, we're just multiplying by 7, right? So the image is going to be all multiples of 7. So, I mean, you could write this a bunch of different ways. So phi of z, I would write this as just 7z. All right, so that's all multiples of 7. You can't get anything other than a multiple of 7 by multiplying by 7, right? Yeah, it's not like you can get the number 2, right? Because 7 times nothing is 2. Okay. Sweet. Now let's look at this companion problem, which is the next one, which says find all homomorphisms Z24 to Z18. So find all homomorphisms from, I'll call them phi, from Z24 to Z18. So this is one of those problems that seems like it might be intractable. It It might be really difficult, but there are some tricks that make it go fairly simply. And so we'll use those two tricks. I'll call them facts. One is that homomorphism on a cyclic group is completely determined by where it sends the generator. So we know Z24 is equal to the cyclic group generated by 1, right? So it's a cyclic group of order 24. It's generated by, well, it's really generated by anything that's relatively prime to 24 by an earlier theorem, but we might as well just use 1. So 1 plus 1 is 2, 1 plus 1 plus 1 is 3. You can go all the way up to 23, right? And then 24 times 1 is 0. Okay, so that's one fact. And then, well, let's build off that fact. So all we need is phi of 1. So a homomorphism on a cyclic group is completely determined by what happens to its generator. So the generator is 1. So all we have to do is figure out where phi of 1 is. Now let's also notice that the order of 1 is equal to 24, right? Yeah. And then now let's look at fact number 2. And that is that the order of phi of G must divide the order of G. You know, previously we used absolute values for this, but I think it's a little messier when you've got this division symbol and stuff. So that was something that was proven in one of the videos, and we used it for that contradiction just a second ago, right? But in terms of our setup, that means that the order of phi of 1 must divide the order of 1, right? Remember that this over here is happening in Z18. This over here is happening in Z24, right? Well, we know that the order of 1 is equal to 24. So in the end, we know that the order of phi of 1 has to divide 24. But we're in luck because it's easy to write down the divisors of 24. So the order of 1 has to be equal to 1, 2, 3, 4, 6, 8, 12, or 24. Right?
Mhm.
So this line right here is because of this. But then because phi of 1 is in Z18, we know that the order of phi of 1 has to divide 18. The order of an element divides the order of a group, right? So that tells us that the order of phi of 1 has to be 1. Well, it's the divisors of 18. So let's see, 1, 2, 3, 6, 9, 18, right? So look at this. From one rule, from the homomorphism rule, the order has to be in this set. From the order of an element dividing the order of a group, the order has to be in this set, right? So if it has to be in both of those sets, it has to be in the intersection, right? So that means we can easily mash those two facts together to get us a smaller set that our order has to live in. So let's do that. So we can maybe underline. So let's see, 1, 2, 3 are possible orders, and 6. Those are the only ones, right? Because that's the overlap. So let's write that down. So order of phi of 1 equals, sorry, is in the set 1, 2, 3, 6. Okay. So we'll just do each of these as cases. So case number 1, the order of phi of 1 is equal to 1. Well, there's only one element with order 1. That's the identity, right? Yeah, the identity is the only thing that has order 1, but this would be the homomorphism phi of 1 equals 0, right? So it has to go to the identity. Yeah. Now, order of phi of 1 equals 2. So that means that phi of 1 has to be sent to something that has order 2 in Z18. So what has order 2 in Z18? So what, when you combine it with itself, you get the identity in Z18. So you need like n plus n equals 0 in Z18. So what's n? No. So what has order 2 in Z18? What's half of 18?
Oh.
9.
Yeah.
So not, so 9 plus 9 is 18, right?
Yeah.
So that means 9 has order 2, right? Because you combine 9 with itself, you get the identity. So 9 is the only element with order 2. So that means that's the homomorphism here. Phi of 1 goes to 9. Yeah. Now let's go to the next one. So order phi of 1 equals 3. Now we've got to find elements that are order 3. So that means you add them to themselves 3 times. So person plus person plus person equals identity. Well, no, 9 plus 9 plus 9 is 27. We're in Z18. So what plus
6.
Yeah, 6. So phi of 1 is 6, because now 6 plus 6 plus 6 is 18, which is 0, but there's one more. It's also 12. So phi of 1 is 12, also works, because 12 plus 12 plus 12 is 36, which is 0, right? Yeah, 36 is 2 times 18. Now, finally, we need to look order of phi of 1 equals 6. So that means we need something, we add it to itself 6 times and we get to the identity in Z18. 3, exactly. So phi of 1 equals 3. 3 plus 3 plus 3 plus 3 plus 3 plus 3 is 18, which is 0. Now there should be one more. So notice 3 plus 3 is 6. That doesn't work, right? Because 6 has order 3. 3 plus 3 plus 3 is 9. That has order 2. But I think if you take 15, you're good. So phi of 1 equals 15 also satisfies this rule. And and we can actually check that. That's because in Z18, the order of 15 is equal to 18 over the GCD of 15 and 18. You can think about that like in the back of your mind. That's that formula or whatever. So, well, but the GCD of 15 and 18 is 3, right? So we get 18 divided by 3 is 6. So that's why that's an easier way to check that 15 has order 6. And you could add 15 to itself 6 times and see that you get back to 0, but who's got time for that? Okay, now that's all your homomorphisms. Now we're done, right? So without doing all of this setup, like where we did this order of the image of an element versus the order of the preimage, and the order of an element divides the order of a group, and all of that stuff, we wouldn't know that we were done. We would just speculate that we're done. But this analysis over here proves that we really have all of our homomorphisms. Okay, So let's maybe like get started on one more and then we'll look at that before we're done. Let's pick it. There. Let's start number 7.
Good.
Yeah. Doing a little stretch. I dropped in 5 out of 6 times yesterday. Only crashed once.
Very good.
It's good, right?
It's all about not leaning forward too much. Or lean back, really don't lean back like at all.
It's all about leaning perfectly. I still get to the other side and I'm like, oh crap, what do I do? I stall up on the side of the board, but then I'm like, oh no, what am I gonna do? And then I jump and run. I don't have it yet.
I did a full 360 rotation with this my skateboard yesterday. On accident.
Nice.
I'm still a beginner.
You fell in your room.
No, I did a whole 360.
Oh, nice.
That was really good.
I helped my friend build his skateboard today. So that's gonna be awesome.
Nice. All right. Let's look at the start of this. So we've got a group Z12. So this is like an example of the second isomorphism theorem in practice. So we've got Z, did I say 12 or 24? 24. And then we've got two subgroups H, and they're calling them H and N. So we've got H is the cyclic subgroup generated by 4, and N is the cyclic subgroup generated by 6. Then let's write these out. So this is going to be 0, 4, 4 plus 4 is 8, 4 plus 4 plus 4 is 12, plus 4 is 16, plus 4 is 20, plus 4 is 24, which is back to 0, right? So that's a 6-element subgroup. Now let's look at 6. So we've got 0, 6, 6 plus 6 is 12, 18, 24, which is back at 0, right? Now let's look at H intersect N. So from homework, or maybe we did it in class, maybe it was kind of a mixture of both. We know that first of all, we know that these are two normal subgroups because they are both subgroups of an abelian group, and we know that intersections of normal subgroups are normal, so that we know H intersect N will be a normal subgroup. So we notice that this is equal to 0, 12, right? I mean, that's just by intersecting sets, right? If we wanted to, we could notice that that is the cyclic subgroup generated by 12. Another interesting thing to notice is that 12 is the LCM of 6 and 4. So there's some like numerics going on there. That, we don't really need that here, but that's something that's going on. Now let's look at H plus N, which usually when you're writing the isomorphism theorem, you write it as H times N because your arbitrary group operation is written multiplicatively, but here we're additive. So we'll write H plus N. So how do we do H plus N? We look at all possibilities of adding something from H with something from N. So we have, let's pick 0 from N first. So we could do 0 plus 0, 4 plus 0, 8 plus 0, 12 plus 0, 16 plus 0, and 20 plus 0, right? So that gives us 0, 4, 8, 12, 16, 20. So that's the plus 0. Now we could do the same thing plus 6, right? So we could do 0 plus 6, that gives us 6. 4 plus 6, that gives us 10. 8 plus 6, that gives us 14. 12 plus 6, that gives us 18, right? 16 plus 6, that gives us 22. 20 plus 6, that gives us 26, which is 2. Right. And now, I think if you add by 18, you're going to get the same thing. I'll let you guys check that, but notice we need to do 12. So 0 plus 12 is 12. We already have that, right? 4 plus 12 is 16. We already have that. 8 plus 12 is 20. We already have that. 12 plus 12 is 24, which is 0. We already have that. 16 plus 12, we already have that. And so we don't need to worry about adding by 12 because we already have all of those, right? And then similarly, we don't really need to add by 18 because we already have those as well. 0 plus 18 is 18. 4 plus 18 is 22. 8 plus 18 is 26, which is 2. And then so on and so forth, right? So this is the entire set. Now I want to notice that that's the cyclic subgroup generated by 2. That's all even elements, right? That's kind of neither here nor there, but it is. And notice that 2 is the GCD of these two. Again, there's some numerics going on there that we won't worry about. Okay, now it says list the cosets on each side. So now we're like sort of running out of time, but essentially what you want to do is look at H plus N mod N. I'm writing it as H plus N. So notice N has 1, 2, 3, 4 elements, right? H plus N has 12 elements. So that means there should be 3 cosets, right? Because 12 divided by 4 is 3, right? So you want to list these, and then you also want to list H mod H intersect N. I'm going to go ahead and write that this is 12 divided by 4. You're getting 3 by doing 12 divided by 4. But now H mod H intersect N, well, notice H has 6 elements. H intersect N has 2 elements, right? So that's 6 divided by 2, which is 3 cosets. So you get the same number of cosets, but you get the same number of cosets by doing different division problems. That's what makes the whole thing kind of non-trivial. And then, I mean, you'll list those just like we listed cosets back in the day when we were doing quotient groups initially. And then finally, you describe the correspondence between the two, because these should be isomorphic, right? Second isomorphism theorem says that these two are isomorphic. And that is, I would just like reread the proof of the second isomorphism theorem to see exactly how it's constructed. And that'll give you a way to send these cosets to these cosets. Okay, so does that seem, we did some work, right? Yeah, okay. So we'll do about the same thing next time. That's right. It's due next Tuesday. Yep. And it will be the last homework. Right? Because that's the last one. There's really no choice there. There's going to be homework due every day of the week, the last week.
Oh, no, that was
Yeah. Just kidding out there in Zoom world if you didn't.